The broadcast is now starting. All attendees are in listen-only mode.
Okay, good morning, everybody, and this is Dr. Mansour, and today is June the 20th, 2020, and this is the AM, the Civil Bridge AM workshop. We still have one more to go, the one I added to make up the class that one day I missed, and this is going to be the 4th of July. So today I do have the Civil AM from 9 to 12. I have surveying today from 1 to 4. This was also added additional surveying class for those who are taking the California special exam. After I finish the course, I added 2 sessions. Tomorrow I have a transportation PM from 9 to 12 and seismic from 1 to 5 tomorrow. So this is this weekend. The following weekend, which is the 27 and 28, I do have transportation construction on Saturday. Sunday, I have construction again, and I have seismic. And finally, the last free session is going to be July the 4th. So all these dates already sent out last week, if I remember correctly. If not, I will be glad to send it again to remind you. So the 7 a.m., which is today, so the 7 a.m. Workshop, and today is 6/20. 2020. I hope that everybody is healthy and everybody is doing fine. And I hope that you are refreshing your memory by studying, by solving problems, and so on. So please do your best. So July the 4th, 7/4/2020 will be the last session for the civil bridge workshops this summer from 1 to 4, by the way, as I mentioned last time. So it is the last session, or last free session, if you'd like to call it that way, or last free workshop from 1 to 4 p.m. All times are Pacific Standard Time or California time, West Coast, as all of you know. Okay. So I'm still behind. I'm trying to do all my best to catch with many things, including the 5 mini exams. I hope that all of you got a chance to work all of them. And as I said that before we end this series of free workshops, you will get my solution, and I hope that this will help you to understand more. If I'm able to do it, to send it to you before July the 4th, this will be the best. At least during July the 4th meeting, the last meeting, we can go over and you can say why this solution that way, why the solution is different, why my answer is different from your answer. I will do all my best. I will do all my best. I'm extremely busy, but this will not forgive me from giving you the solutions for the mini exams 1 through 5. There is another chapter, and I don't know if I send it or I ask one of my assistants to send it to you. If not, I can send it during the break. And probably I mentioned this chapter. This chapter, by the way, I wrote it, I don't know, about a year ago or maybe more or less. And the chapter has a title of materials, like chapter 7 of the civil breadth reference manual, my textbook for the civil breadth reference manual, the AM. Chapter 7 is called also materials, which is, according to the NCEES, theoretically speaking, you're supposed to get 6 questions related to materials. A parallel chapter or a chapter going on in the same direction, almost. It is for the FE, the Fundamental of Engineering exam, or it used to call EIT before. And I prepared this chapter, and I found this chapter is really, really useful. Even I gave it to the PE group also. So I can say this is FEPE because the FE Civil, they are covering, or they are testing them almost the same material for the PE, even more, by the way. The FE Civil, okay, they are testing them, or they are covering more topics than the PE, by the way. If you compare it, you will find this statement is correct. So there is some kind of overlap, but the FE, I believe it is having more addition. So when I prepared this chapter, and I discussed it with the FE group who attended the class before, and hopefully that this book, I don't know when it will be out, but I started 2 years ago and I'm still working. I did not finish it yet. Even they are going to change the FE July 1st, 7/1/2020. They are going to change the arrangement of the topics. Instead of 18 chapters in the old one, right now they became 14 chapters. Anyhow, I will send this chapter to you. If I did not send it, okay, I will send it during the first break. But basically, the topics that covered under the NCEES, mixed design, which is required for all of you, either concrete mixed design or asphalt mixed design, test methods and the specifications. You need to know the testing for steel, concrete, aggregate, asphalt, wood, and so on. And physical and mechanical properties of these materials. Testing is very, very important, and materials in general, as the title of the chapter, is important, and testing and knowing the properties. I received one question from one of you. I don't understand the question, even it's typed from another source. It's asking about the maximum tension for RCC beam. The question like this, I will bring the print of this question next time. I don't understand I know that RCC by itself, there is rolled compacted concrete. This is another type of concrete. We use it for dams. But the question is a little bit not clear to me, so I did not get a chance to respond back to the engineer who sent it to me, but I will. But I did not really ignore any question. If you send a question to me, I will do all my best to come back to you as soon as I can. So he got this question from somewhere, the maximum tension is, and I really is not clear to me. So I will look at it and come back to you. So when we look to materials, which we talked about it last time, materials. We need to make sure that we are understand the properties of these materials. And materials for the PE, they are expecting you to know properties of concrete and steel and asphalt and wood, and probably I will add masonry to it. We can talk a little bit about masonry, the CMUs, or bricks, okay, masonry in general, okay, concrete masonry unit, CMUs, and bricks. Okay, I taught one class here at CSU Fresno for masonry design. We have a very nice textbook available in the market, and below some of you use it. Wood also, I taught wood for about 20 years. Asphalt, steel, concrete, all these things, they are expecting you to know. The equations and the properties are very, very important. Some of these materials, they have equations related to their properties. For example, for concrete, we should know that the F sub C prime is equal P over A, which is the uniaxial stress for the cylinder, the famous cylinder, the 6/12 or 4/8 after we, and we should know that. And this is a 28-day compressive strength. Okay, we should know that the F sub C prime, this one here, is supposed to be at 28 days. So this is the 28-day compressive strength, the one we use it for designing beams and columns and so on. Under concrete, also you're supposed to know the modulus of rupture. The F, sometimes they call it sigma. F sub R. Let me double check because I need to stick with the ACI abbreviations, so I don't like to use normally. If, for example, all these based on the ACI, American Concrete Institute, so I always stick with the abbreviations as much as I can. So that's correct. F sub R is correct, is the correct one. So the F sub R is correct. We call it modulus of rupture. Modulus of rupture. Modulus of rupture. And the modulus of rupture, it's calculated using this equation, MC over I, the bending stress formula or flexure stress formulas, but they call it MOR or modulus of rupture or modulus of rupture, sorry. And so this is number one and this is number two, or sometimes we call it the beam test. Beam test, where they have a beam and you might be given like this on the exam, they will give you a beam. And the cross section of the beam is given, B and H. And if this is, for example, this is 6, normally this is 6 by 6, by the way, 6 inches. And the load is delivered using what is known as the third point loading. So if this is a maximum load here, so B over 2 here and B over 2 here, where the load is applied at 1/3. So this is L over 3, L over 3, and this is L over 3. This is called third point loading. Point loading. Let us assume for the sake of discussion, B is, let's assume that L is equal, L is normally 30 inches, by the way. The clear span is 30 inches, okay? 30 inch. Sometimes we make it longer than that. Sometimes, okay, but let's assume for the sake of discussion that this beam is 30 inches and it's 6 by 6, and let's assume that the load here is let us at least to get something a little bit reasonable, assuming that that the load is about 4,800 pounds, or make it 5,000 pounds. This is the failure load or maximum load, failure load. Okay. Based on that, can you tell me what is the MOR? The MOR, or the modulus of rupture, MOR, and the 30-inch is the span length, and the load is loaded at the 1/3 point loading, or the 1/3. Can you tell me what is the MOR? Let me give you 1 minute only. You calculate it for me. And this is 6 inches by 6 inches. This is concrete. Unreinforced beam. Normally it is unreinforced. Is a plain concrete. And if the load is, maximum load is recorded from the testing to be 5,000 pounds, and the cross section. Can you calculate what is the MOR, the modulus of rupture, or we call it F sub R, which we take it as indirect test for tension properties of concrete, or for tensile properties of concrete. Let me give you 2 minutes from now. Right now is 9:18, so I will stop to 9:20. And let us vote. We are a democratic country, so we're going to vote this coming November. So November the 3rd, as I mentioned last time, that we have election November 3rd. So let us come up with some answers, and we'll see what is going to be so L is equal 30 inches, and the load is 1/3. Okay, so third point loading, and the dimension is 6 by 6, 6 inches by 6 inches. This is 30 inches also. Okay, so let us get some answers from you. Let us see what is the first number. What's the difference between concrete modulus of rupture and concrete modulus of elasticity? Yes, there is a huge difference. I will talk about that. The MOR is just, okay, we are going to calculate it. I got a number from one of you. Give me a number. No, I need a number. You are giving me an equation. The equation you are giving me, my friend, is the ACI equation. This is an empirical formula, but I need a number. I need how many PSI. I will talk about this, Muhammad. This is actual testing. This is what you see here is actual. I need a number. I got a number. Maybe it's okay. Give me a number. Okay, so okay. Pound inch units are very important. I have PSI and pound inch. The correct units are PSI. So I got 694 from two of you, and I got some different answers. So the modulus of rupture, MOR, it came from the beam test. And we use the modulus of rupture as a measure for, this is indirect measure for tensile properties of concrete. Tensile properties of concrete. Concrete is very weak in tension, as all of you know, and strong in compression. But we need to determine the tensile strength of concrete. So there are two tests. It's called indirect because there is no direct test. And I will explain this one more time. But let's take one step at a time. So the MOR, modulus of rupture, or F sub R as ACI use it. It came from this MC over I. Okay. So what is the moment? If this is 5,000, that means that the reaction here is 2,500 pounds, and the reaction here is 2,500 pounds due to symmetry. Symmetrical, half of the load will come in this way. And the maximum bending moment will be here, by the way, which is 2,500 times 10 inches. Why 10 inches? Because the entire span length L is equal 30 inches. So 10 and 10 and 10. So the moment is 2,500. And this is bound, the reaction, times 10 inches. So this is bound inch. What is C? C is defined as the distance from the neutral axis up to the extreme fiber. The neutral axis for this beam in the middle, N sub A, or NA, sorry. NA, not N sub A. So right now it is 6 inches. So that means that this is 3 inches top, 3 inches bottom due to symmetry. So I will multiply C is equal to 3. Divided by I. I for this one here, I, this is a rectangular section or a square. So all of them, they go with this equation, BH cubed over 12. So B is 6 inches and H is 6 inches cubed divided by 12. This is in inches. So this is inch to the 4th power. And the 3 inches, by the way, at least to come up with the units. Because this is bound and this is inch and this is inch. So it is bound inch square. And okay, bound inch square. Here, inch to the 4th. This way we ended with PSI, pounds per square inch. So if you do this simple math, this number is not a strange number, 694. So it is 2,500 enter, and 30 times, and 12 times, and 6 enter, 4y, and divide. So I got 694.4 PSI. This is the modulus of rupture. It is a small number, as you can see, 694, okay? Because the concrete that will produce this amount of modulus of rupture, by the way, this F sub C prime, if you prepared a mix from the same material that is used for this beam, and you prepare cylinders and test it according to ASTM, by the way, this is ASTM C39. Each test, it has a number, as you know. The American Society for Testing and Materials, they assign a number. C for cementitious materials, and 39 is the number. This, for example, the beam test here, this is ASTM C 78. And I will double check these numbers. I remember that these numbers are correct, but so if you have the ASTM, the American Society for Testing and Materials, there are 64 books, and these books, they explain how to do the testing according to the standards. So if you do ASTM C39, which is a compression test, this is a compression test, to determine the compressive strength of concrete, which is F sub C prime. If you prepare the cylinder or the cylinders using the same mix, you may get a number in the neighborhood at least, excuse me, maybe 5,000 to 6,000 psi, at least psi. Remember, this is 500 pounds. This is the failure load. This is a stress. So 5,000 or 6,000 psi at least. Okay. Because let me move to the second page here and try to explain this. Because F sub C prime, as I told you, it will be, I don't know, it's not given to me, but at least between 5,000 to 7,000 psi. Because the ACI, the American Concrete Institute, the blue book or the blue code, they came up with the empirical formula, the one that Muhammad is referring to, that we can determine the F sub R using the empirical formula that's given. So they came up with that F sub R is equal to about 7.5, and I say about because this is an empirical formula. This is an empirical formula. If I am not able to perform the beam test for whatever reason, I don't have the capability, or I don't have the testing machine, or you are in the field. You are in the field and you don't have this setup for the beam test. It's called the beam test, or bending test, or a flexure test, or modulus of rupture test. Okay. If you don't have the setup, or you don't have time, let's assume that you have the capability to set up, but you don't, and you need to estimate the F sub R very quick, so we can use the empirical formula. So if you plug the, let's assume, just I'm guessing this number, okay? Let's assume that it is, if we take, I don't know what this number, the real I'm saying is between. So let's assume 5,500 PSI is my number here. So it is 7.5. And since this is an empirical formula, units doesn't work because you are going to put PSI under the radical quantity, so 5,500. So if you do this, assuming that the 5,500 is the number that's given to you, 5,500, take a square root and multiply by 7.5, you got about 556, okay, PSI. Okay, it is a number. If we know the exact number here, if you put the 6,000, maybe you are getting close, okay, to the 694 pounds. But so we use this as an empirical. This must be given to you. You cannot assume it just. But here I just guessed. Okay, maybe between 5,000 to 6,000 psi. The reason that I guessed, and probably my guess is not exactly right, that the F sub R, the modulus of rupture, is about, again, is a range. It is 10% to 15% of the F sub C prime. So if we take 6,000 and you say 10%, probably 600 psi. If you are going to take somewhere in 15, so maybe this one. So this is the range of the modulus of rupture as a function of the F sub C prime, about 10 or 15% of its compressive strength. So the tensile strength of concrete, this is a measure, tensile strength, and this is a compressive strength. Is about between 10 to 12%. 10 to 15% at the most. 15% this is okay. So this is a very low, and this is a very high. This is a highest. So this is a very wide range, and this is the range that normally some people they say that I will take it as a 10%, a 12%, and that's it. Okay, that's fine. I have no problem with that. It's a range. Nobody will blame you, but the actual testing will. But we use this empirical formula in order to estimate. So, and in design, the ACI code, we ignore the 10 to 15%. We are saying that the concrete will carry zero tension stress or tensile strength. Concrete will carry zero tension. So in design, okay, the ACI code, they say that concrete will carry zero tensile strength, or it has zero tensile strength, or it doesn't carry any. And you remember this from the stress block, which I mentioned at one time before, that if you do have a rectangular beam, and this rectangular beam, it does have reinforcement, as shown here, okay, the tensile rebars. So we do have the Whitney stress block, and we are saying that the tension is here, T, at the centroid of the rebars, and there is a block here, it's called Whitney stress block, and the C, which is a compression, which is 0.85 F sub C prime A times B. B is the width, by the way, of this. And this is D. This is the effective depth. And we call the entire depth is H, by the way. But the D is to the centroid of the rebars. So this C is 0.85. So below this, all this concrete, it'll carry zero tension. This is a compression block, and so from here to here there is nothing. We assume that's vacuum. There is no anything here, and we draw the neutral axis and so on. So this is, however, why we need to do this? Why we do the beam test? Either if we can do the actual beam test, prepare beams and test it, and you get M sub MOR. This is one test, by the way. There is another test is called splitting tensile strength. I mention it after I finish this. Why we are interested to know what is the value of F sub R, either from the empirical formula or from the actual test. Because when we do some slabs, especially for highways and streets, concrete slabs, the PCC pavement, whatever, okay, these slabs, under the effect of the load or loads coming from the trucks, the e-cells, the equivalent single axle load, as all of you know, the loads, the tire, okay, whatever the truck or whatever. So these loads, what will do with this, what will happen to these slabs? These slabs we are expecting to do this. It will concave like this. So this is the tire load, either this one or this one, whatever is convenient to you. So this is compression and this is tension. So the bottom of the concrete slab is going to be under tension. So we need to know at what level the cracks will start to generate along the tensile. So we need to know that. This is why we specify for pavement, we specify the F sub R. Even we know that the concretes are not supposed to carry any tensile, but I need to know what level, at what level the concrete start to have some cracks along the tension side in order to design a very good structure section such that this concrete will resist the loads with minimum cracks, because the cracks, the water will go in and start to create problem for the pavement, and we notice that. This is why nowadays we are using what is known as a CRCB. Continuous reinforced concrete pavement. CRCB is a very common right now. It's very expensive. Or we put rebars in both directions, and CRCB, or we put sometimes we put dowels and so on. But in a CRCB, the continuous reinforced concrete pavement, and some of you already probably have some project already work on the CRCB, where we are putting rebars in order to ensure that this concrete will last, because concrete is very weak in tension. So the rebars, in order to extend the life, especially along the tension side, because the concrete is very strong in compression. So the rebars is going to help to resist the tensile stresses and so on. So I needed to know that. Before I leave this drawing, I draw something here, 2 lines, we call them datums. Can you draw the shear moment diagram or the shear and moment diagrams for this setup, for a beam that is loaded with these loads? Can you tell me, and let's assume this is 5,000 pounds, and I assume. Can you sketch the shear moment diagram very quick? Let me give you another 2 minutes, because we need to know that. Okay, the V is the shear force, is in pounds. Moment are in pound inch. Force time distance. So the loads are given in pounds, and the distance are in inches. This is why the moment is equal force time distance. So the shear diagram is going to be like this. I have 2,500. I will go up 2,500, and I will go straight. And I will tell you why we go straight. And I will hit B over 2, which is another 2,500, will bring me down. And I will move horizontally 0 in the middle third. And after that, I will go down, 2,500 again, and until I hit the other reaction, and will close the shear diagram. So the shear diagram here is positive, and the shear is negative, and this value here is 2,500 pounds. Already I put the units pounds here based on 5,000. This is given to you, by the way. Failure load must be given. Don't assume it. It must be given. Must be given. Okay. So, and this obviously 2,500 also. So this is the shear diagram, and the shear in the middle is 0. No shear in the middle. Why this is straight? Because there is no load between here and here. And we have 2 important relationships. I'm sure that you remember them, which is dV by dx is equal negative W, and the second equation dm by dx equals V. These 2 equations, if we remember them, we should be able to draw any shear moment diagram exists on Earth. Okay, these 2 relationships. So the slope of the shear diagram is equal to load. The slope of this line is 0 slope, because there is no load from here to here. Okay, so come to the bending moment. Is the bending moment going to be positive or negative? Because when we draw this line, which is called the datum or reference line, anything above this reference line is positive, anything below is negative. They agreed on that. Your grandfather and my grandfather agreed on that. Let's keep it this way. Let's come to the bending moment. Is the bending moment going to be positive or negative? Is going to be completely positive. Okay. So the bending moment diagram is going to be positive from the beginning to the end, from point A to point B. And if this is point C and this is point D, so the bending moment diagram is going to be like this. Try to squeeze it in here. This is horizontal, has a zero slope because there is no shear, and it is linear from the supports to the maximum. So this is a positive bending moment, okay? And the maximum value here, which is Mmax, is 2500 times 10. So it is 2500, and another zero is 25,000 pound-inch. And the moment here is zero, and the moment here is zero, and this has a zero slope because dm by dx is equal v. The slope of the bending moment diagram must equal the shear. The slope of this line is positive, and that's why the shear is positive. The slope of this line is zero because the shear is zero. The slope of this line is negative because the shear is negative. So these two relationships, which let me write them on the following page also, just in case if they are not able to read my Egyptian handwriting. So it is dv by dx equals negative w, the load, and dm by dx equals v. These two relationships are very, very important to draw the shear moment diagram for any given beam. And probably after the break, I can bring a problem. I will draw it for you, and I will give you 2 minutes, and you can draw shear moment diagram for me and see if you are going to get it. These two relationships are very, very important. Okay, so let us go to the question that what is the difference between modulus of rupture and modulus of elasticity? Okay, so the MOR and OME. This is the modulus of rupture. Modulus of rupture. And this is the modulus of elasticity. Let me put it in a table form. Engineers, they enjoy tables, okay? And diagrams and figures and illustrations. As far as units, this is PSI or Pascal or megapascal. I have no problem with that. This also in PSI or Pascal or megapascal. So units are essentially the same. PSI, sometimes we use KSI, but very rare. Okay. Also here will be KSI also, Kibs per square inch. The modulus of rupture determined in the lab from the lab or the field, by the way. Sometimes we do the field testing for the cylinders, for the beams, sorry. Determined in the field / the lab from the beam test. This is determined, okay, in the field, if there is a field mobile lab or the lab, okay, from the cylinder test. Cylinder test. Okay. There is one test, it's called the cube test, but we don't use it in the United States. Canada, they use cubes, but in the United States, we don't use cubes. So the cylinder, so the equation F sub C prime is equal P over A. And this is why you will find that in the NCAA's book, and some of you already saw this problem 10,000 times. Let me make it 10,001, and forgive me for that. If you saw it 10,000, make it 10,001, please. Okay. And I will give you 22 seconds to do it for me. I think it used to be here. I don't know if, unless they took it out. No, here it is. Still there. Here it is. A problem 134. Let me give you 22 seconds to do it. Problem 134. This is a blue book, by the way. The transportation or construction or geotechnical or water resources, whatever book you have, all the 40 problems of the AM are essentially the same, notice. So, a problem 134, please. If you don't have the book, here it is. Okay, so sample concrete cylinders that are 6 by 12, 4 by 8 also we are using, by the way, 4 inches by 8 inches also. You might see them on the exam. As long as the ratio H over D must be 2. This is 12 over 6 is 2, and 8 over 4 is 2, and there is a reason behind that. So H over D ratio, H over D must be 2. Something from the theory of elasticity. If you go to the grad school and do your master's or PhD, you'll cover theory of elasticity, and we discuss this in the why the H over D must be 2. The height to diameter ratio must be 2. So this is H, and this is D. So in our case, this is 12 inches, and this is 6 inches. So H over D, okay. And he gave you the axial compressive failure load. So we carried the test all the way up to failure, and he gave you 3 values. And he's asking what is the F sub C prime, which is a 28-day compressive strength. And they probably heard the joke before, why they made it 28 days, why? So nobody will come to work on the weekend. Because if you prepare the cylinders from Monday to Friday, so the 28 day will be also from Monday to Friday. Unless if you prepare the cylinders on the weekend, you have to come on the weekend. But there is no, this is a joke. But the reason that 28 days, that has nothing to do with the weekend, it is just the date that they agreed upon in order to make sure that the concrete gain a strength such that when we apply the load, we are achieving, okay, 100% of F sub C prime. And they did testing and they came up with this date, okay? So the F sub C prime, which is B over A. A problem like that, you don't need to open a book. You don't need to open any reference because this is already stored in your brain and you are able to. So the load, we have 3 loads. We have 65, 447 plus 63617 plus 69139, and I will divide by 3 because I will take the average. So the average load over the area. Area is by D square over 4, or it is by R square. So it is by the diameter is 6 inches square over 4. And you'll get a number and you will select the answer from here, whatever the number is. The H has nothing to do with the calculations because this is axial load. Axial, the word axial, you are using axial. Axial because the load is coming this way. The load is applied to the cylinder, okay, perpendicular, because this axial load, P, the area, it must be perpendicular to P. This is the load, P. And where is the cross-sectional area? Here it is, the area of the cylinder. So the load is perpendicular, or the area is perpendicular to B. So whatever the number is, it must be, okay, matching one of these numbers here, which is average. This is why the word, okay, the word average is very important. Average 28-day compressive strength in PSI. And if you go to the ASTM C39, they will tell you how to perform this test. It's very important to know how to perform the test. They tell us how to prepare cylinders, how to prepare the testing machine, what testing machine is, the rate of loading, how fast we apply the load, what is the temperature of the lab, what is the humidity of the lab. So in order to standardize everything, ASTM must be followed. So if I did a test in California and somebody did a test in New York, since we are using the same test procedures and the criteria and conditions, we can compare results. Okay? So this is called F sub C prime. So I will go back again to this page to ask you a question. So this is B over A. This one here, the modulus of rupture, is determined as F sub R or MOR, if you like to call. This is the F sub C prime. MOR is equal MC over I. So I determine this. This is F sub C prime to get modulus, the 28-day compressive strength. But I'm talking the modulus of elasticity. How can we determine the modulus of elasticity from the compression test? We do this. I have the cylinder, and we do what is known, we have something called compressometer. It is a steel cage. We put it around the cylinder and the screw it. It's called compressometer or compressor meter. It does have a dial gauge, and as I apply the load, I collect what? I collect the load P versus delta. Delta is going to be obtained from this gauge. There is a dial gauge we call delta. Deformation over this gauge length, by the way, this is L. The compressometer, this is 12 inches. Normally this compressometer, it has a gauge length of 8 inches. Some of them are 6. Okay, 2 inches at the top and 2 inches at the bottom. So B and delta. So delta, if I divide it by L, will give me strain. B over A will give me stress. So basically, I'm plotting stress versus strain. In fact, F sub C prime is a stress, by the way. And I will plot this curve. It will be coming like this. This, what we call it F sub C prime. And this number is about 0.002, by the way, inch per inch. So the maximum here, this is F sub C prime. The modulus of elasticity, we determined it from the cylinder test. After we do the cylinder test and collect the load versus deformation, delta, by the way, is called deformation. Deformation. Modulus of elasticity had 3 definitions. Modulus of elasticity, we call it E sub C. We have initial and tangent and the secant modulus of elasticity. There are 3 of them. Initial and tangent and the secant modulus of elasticity. And in my book in chapter 7, there is a diagram showing that. But we are going to stick with the modulus of elasticity as adopted by the ACI. They are saying that if I come here at F sub C prime divided by 2, F sub C prime divided by 2, half of F sub C prime, and they draw a tangent to the curve, because this is a curve. It has a little bit linear here, but it's a curve. The slope of the line tangent at F sub C prime, we take it as a tangent modulus of elasticity. And the tangent and the secant is very close, because the secant will connect this with the origin, by the way, origin 0 here. So anyhow, we determine this from the stress. This is called a stress strain curve. Stress strain curve. And E is going to be what? Is going to be delta sigma over delta epsilon. Okay, because the slope of a line I take two values, okay, along this line. This is delta sigma and this delta epsilon, okay? So, or simply sigma over epsilon, modulus of elasticity. And this is, we call it Hooke's law, by the way. Hooke's law. Here, we determine this from the beam test. As the problem, we solve it together. It is like this. And we use third point loading, not the center point loading, for a reason. We used to have a load in the middle, but they get rid of this test. Okay, this is in PSI and PSI or KSI. This here, the number here, the F sub R, is about, as I told you, between 400 maybe to maximum 700 PSI. But if you look to the modulus of elasticity E sub C is between 2 to 7 million PSI. So the difference is huge. This is in million, this is in 100, 400. So modulus of elasticity between 2 million to 7 million PSI. It depends on the F sub C prime. They have an empirical formula here, the one I mentioned. The F sub R is equal 7.5 is equal to F sub C prime. This is an empirical formula. Empirical, okay, equation or formula. Empirical, I missed I here. EMPIR, empirical formula. This is also by the ACI. The modulus of elasticity also, it does have an empirical formula. It does have an empirical formula, which is given by this equation, which is E sub C is equal 33 W 1.5 is square root of F sub C prime. Or we use for normal weight concrete as 57,000 square root of F sub C prime. Also, this is an empirical formula, empirical equation, or empirical formula. After a lot of testing, they came up with this. So this is 2 to 7 million PSI. This is just only 400 to 700 PSI. As we mentioned, the units. This came from the cylinder test. This came from the beam test. We use this, the F sub R, for what? What we are using this for? We're using for the pavement design. Pavement design, mainly for pavement design because of the cracks that will be developed into slabs on the freeways. Okay? Or sometimes the slabs on grades for houses, slabs on grades also. This another application, like the houses. Okay, if your house, it is on a slab, so we specify the compressive strength and we specify also F sub R, because I don't like the slab of your house to start to crack, because after we start to use the slab, so probably it will concave a little bit down, so we don't need the cracks to start develop. Okay. Also at the same time, the E sub C, what we use E sub C for? Why we determine this? Why we determine the modulus of elasticity? Okay, for concrete, what is the benefit of that? We know the benefit of F sub R, so can determine, okay, the cracks that will be developed. The modulus of elasticity, you will find that the deflection equation, and all of you are familiar with this deflection equation or deflection calculations, and and you might be given a problem, and I believe I have one problem, if I remember correctly, and I ask you to solve it. I don't know if you did solve it or not. So the E sub C, normally we put C, by the way, modulus of elasticity for concrete, which is, I said, about between 2 to 7 million psi. A range, because it's a function of F sub C prime. The higher the F sub C prime, the higher the modulus of elasticity. So what do we use the modulus of elasticity for? For concrete. Why we need to determine this? Either in the lab or using the empirical formula, as I mentioned. If you don't have the testing, if you did not have the capability of doing such testing, and you know what's F sub C prime, so I plug it here. For example, if this is 5,000 psi, so if you look to this, if we take the F sub C prime for the sake of discussion of 5,000 psi, so what do you expect for the mass of elasticity? It's 5,000, and take square root, and you multiply this by 57,000. So it came about 4.03 million psi, about 4, okay, 0.03 million psi. Okay, so I needed to be aware of that. So the use of the modulus of elasticity, we use it for deflection calculations, because the deflection, as given in steel manual or any other books, or including mine, deflection calculations okay, very, very important. Let's assume, by the way, I have a diving board in your house, swimming pool, you have a diving board, and let's assume I would fix it just for the simplicity. This diving board, they fixed it from one end and they free from the other end, and here is Mr. Mansour or Dr. Mansour. Okay, let's assume 200 pound at the free end of the diving board, and here is a swimming pool. He's going to jump into the swimming pool. If this diving board, or this here, is made of steel, and another scenario said that Mr. Mansour, steel is very expensive and it might hurt, okay, you use aluminum. And the same gentleman, Mr. Mansour, 200 pounds, assuming that I am way less than 200 pounds, by the way, so don't, but assuming that to make it easy for you. So if this L here is 8 feet, and this 8 here, L here is also 8 feet. Or make it, it's very short one, 8 feet short, make it 14. Make it reasonable diving board, here it is. And the cross section here is 12 inches by 1 inch thick. And I made this also 12 inches wide by 1 inch thick. But this is steel and this is aluminum. And the same weight at the tip of this, assume this is a concentrated load. I will be putting my couple feet, okay, into the tip of this. So we are expecting that when I step at the tip of this diving board, it will come down. And the same story, it will come down. So this is delta 1 or delta steel, and this is delta 2 or delta aluminum. And I will go back again why I'm mentioning this in relation to concrete. I didn't make the diving board of concrete, but this, if we understand this, this will be applicable to concrete and to any other material. Do you expect that delta 1 equals delta 2? Or answer B, delta 1 greater than delta 2? Answer C, delta 1 less than delta 2? And answer D, that delta 1 is equal or about 1/3 of delta 2. This is the first question I am going to ask. Can you read my... The second question I will ask, what are these values? A, B, C, and D. Okay, so I need two numbers. One for the steel, how much is the absolute the value, and one for the aluminum. But before we take the first break, let's answer this question here. And let us vote. We are a democratic country, as I mentioned, that is delta 1 equal delta 2, or delta 1 greater, or delta 1 less, or delta 1 is 1/3, about 1/3 delta 2. And normally, if you are getting these kind of questions or conceptual questions, we are looking for the best answer, best answer. Maybe a couple answers are close to each other, but there is one is the best. And this is the case, by the way. Because if you look to the two answers, C and D, it's telling me delta 1 is less than delta 2. But he's telling me delta 1 is about 1/3 delta 2. So they mean the same thing, that this is less than this. But he's telling me this is about 1/3, but still less than delta 2. It is only 1/3 of it. But among these two answers, there is one is the best. Okay? If we know the delta equation, either delta uppercase or delta lowercase, by the way, whatever is convenient for you, delta, some books they are using even V, like NCEES, they were using V in the past. I don't know if it's still using this delta. Let me just erase this here to make it just delta without specifying delta. So delta, some books they are using delta uppercase, some books even they using V, which is a deflection. The deflection is a function of, or the deflection depends on what, or a function of what? Of some parameters. If I know these parameters, I should be able to answer this question correctly. So already I gave you 50-50 because I eliminated answer. Delta 1 is in fact less than delta 2. Delta 1 cannot be, they cannot be equal. This is wrong. And this is wrong. So delta 1 is less. But I added another answer here. I said delta 1 is about 1/3. And this is the best answer. So if this question is given to me, I will select this. Delta 1 is the aluminum one, when the diving board is made of aluminum. Why? Because delta, for a situation like this, for a cantilever beam that it has one concentrated load at the end or at the free end, as shown, is PL cubed divided by 3EI. This is the equation that you see it in steel books or steel manuals and or my books. I will show it to you, or in other book available in the market. You will find that I said that the load P is my weight, and I assume my weight is concentrated load. Sorry, somebody is asking about the classes and so on. Okay, so PL cubed over 3I, if you look to Any textbook you'll find, or any review book, you'll find this. So the load is a concentrated load. L is the same, B is the same, 3 is the same. I made the cross-sectional area to be the same. That means I is the same. So we're talking about E. So the deflection is inversely proportional to E. So delta is inversely proportional to 1 over E. The larger the E, the smaller the deflection. In the denominator here. So for deflection calculation, I need to get E sub C, the Modulus of Elasticity for concrete. Okay. So this question here, if I know E steel and if I know E aluminum, I can say the ratio between them is the ratio of the deflection, because all the other parameters as far as a P and the L and the cross section, which will give me the moment of inertia or the second moment of area. So E steel is constant number, by the way, 29 million PSI. They remember the E concrete between 2 to 7 million PSI. Steel is 29 million PSI. E aluminum is really not constant. Varies between 8 million PSI or 8.6 in fact. 8.6 million PSI to 11.3 or 11.2. So, but normally we say E aluminum is about 10 million PSI. It's acceptable to use this number for the sake of calculations, unless he give you the type of the aluminum alloy. Exactly, I can go to the references and I can show you that to get the exact number. But steel, it doesn't matter what steel is. A36 steel or A54 steel, name it. All kinds of steel, still one number we deal with it. So we can say roughly, we can say that E aluminum is about 1/3 of E steel. So, and this is why I use the 1/3, which is 10 million and 30 million. Even some books, they are using 30 million instead of 29 million, still acceptable, but the steel manual is using 29 million. So here, this is the best answer as far as I know, delta 1 less than delta 2, but here he's giving me some numerical values that are within the acceptable range. So this answer D is the best answer among, even answer C is still a correct answer, but this is the best. This is the best. Okay. After the break, I'm expecting you are going to work what will be the delta steel and delta aluminum based on the given information. Okay, based on the 200 pounds at the free end, 14 feet, 1 inch by 12, and the Modulus of Elasticity, 29 million PSI and 10 million PSI for steel. Let's get some numbers to see how many inches here and how many inches here. Okay, using this equation, already I gave you the equation, PL cubed over 3EI, because I am expecting that we may mess up with units. Units are very, very important. Okay, let's take a few minutes break. Right now is about 10:15 California time. So 10:25 we'll be back with open mind and open heart and continue our discussion. Okay, and I will send right now this chapter. At least if we are not able to get in it today, I hope that I can jump on it. I have about how many problems? I believe I added a lot of problems. About 49 problems. 49 problems. All of them except 2, they are related to the PE. 2 of them are related to the FE, but it is like, for example, this problem, the thermal deformation, maybe is not directly related, but you have 47 problem if we excluded 2, okay? One is related to what is known as the modular ratio. If you remember, the N, which is, we're going to see it, we'll talk about this. We'll talk about this later on. Okay. So let me go and email you this. It is a chapter materials. A very, very. I did my best. I cannot claim anything other than that I did my best. Okay. So enjoy your break, and after I come back, I will answer you. I think one of you raising the hand right now or asking a question. I will be glad to address all the questions after we come back from this short break. Okay. So right now is about 10:16 or 10:17. Let's make it 10:30. Thank you very much. Okay, I scanned the file, the chapter 9. The scanning quality is not great for some reason. I don't know why. So I will send the PDF this afternoon. I don't have access to it right now, but I send the entire chapter to you as a scanned document. And if you did not receive it, please let me know. I will be glad to send you. I will get the PDF from the other computer, and it will be better quality, no doubt about that. Okay. But I send it just in case if you'd like to print it right now and study, or use it until we meet next meeting, will be fine. Before the break, we were talking about this. And let me go to the question first, because some of you raised a question. And what's the question here? Let me go all the way down to the, I know there is a lot of, delta is equal 1/3, okay. So how can I find the latest classes? My name is Alex. My email is so and so. Whatever, everything on our website. All the free classes, they are recorded and they are posted on our website. Okay, if you go to the website, all the classes that will come this fall, it is also available on our website, the civil, transportation, construction. If you have any specific question, email me and I will reply back to you. So this is the best way to get. Go to our website, and if you allow me to go very quick, I believe, and here it is. Let me. Here it is. So this, for example, to sign up for the free classes. And here, this is a free workshop videos. If you click on it, it will take you our classes, on-demand classes, live classes. So if you have any specific question, or if you are not able to get access to anything, or the website is not does not have enough information, normally we try to improve our website or my website. I don't do that, but I will keep working on it. I know there is always area for improvement, but email me and I will be glad to guide you or tell you whatever questions that you have. Okay. So going back to our discussion here, so if you go to the website passpe.com, I believe you should be able, but if there is any missing information or any incomplete information or any information you are not able to get access to it, please let me know and I will do my best. Thank you. So going back to the discussion here about the steel and the aluminum. I don't know if you get a chance to calculate the steel, the delta steel, and delta aluminum in inches. Obviously, we need to get them in inches. So did anybody find a number, or did you get a chance during the break? I know probably you were also tried to take. So he said that aluminum 31.6 what? 30 point, steel is 10.9. Steel, I got a number 10.9 inches. I assume that. Okay. And aluminum is 31.6 inches. I assume that these are in inches. I got a couple answers so far. Anybody can support our friend, or steel is 10.9, okay, and aluminum 67.2. So aluminum, so this is 10.9, and this is 67.2 inches, as our friend suggested here. If sorry, steel is 23.2. Sorry, 23.2. 23. 20. So I have 23.2 and 67. Okay. Sorry, my friend, I mix your number with another number, but I have 31.6 and 10.9, and the other 67, 31. So you can say the ratio from here to here, is about 3, and the ratio here is about 3. So the third, I mean the 1/3, or this is 3 times of this and 3 times of this. But which number is the correct number? Let us get another answer here. Aluminum, 94.8 inches. The answer, give me a number, 10, okay, 10.8. I got 10.89 again, and I got aluminum 32, aluminum 94. I have 94 inches, and I got 32 inches for aluminum, another 32. That's close enough to 31. Okay, so it seems to me that we do have a little bit of numbers here that are not. So let us do it together very quick to see what. And as I told you, units are very important, and as far as taking care, everything is important, but units, we need to pay attention to units, because sometimes we do mistakes because of the units. So we said that it is delta steel. Start with delta steel, which is PL cubed divided by 3EI. So P is 200 pounds. This is Mr. Mansour. Okay, L is 14 feet. I'll multiply this 12 inches per foot. And this is cubed. Divided by 3. E, I will use it as 29 million PSI. Okay. And the I, since the cross section is given to be, it is 12 inches by 1 inch. So it is BH cubed over 12. So it is 12. Okay. And this is 1 cubed divided by 12. So if we do this piece of calculation, unless I did a mistake here, if somebody can tell me what mistake I did, if I did any mistake, PL cubed over 3I. So it is 14 enter 12 times and 200 times, and the 3 divided, 29 divided, and 10 to power 6 divided, 12 will cancel. So I got 10.9 inches. This is delta steel, or delta steel, uppercase or lowercase, both of them are acceptable. If we did the same thing for delta aluminum, so it is the same, it is 200 pounds. This is a load, concentrated load, times 14 feet times 12 inches per foot cubed, divided by 3, and I will use 10 million PSI, and again 12 times 1 cubed, 12 inches 1 cubed divided by 12. So in this case, this is 10, and this is, so we're expecting this to around 3 times. So this is, will go this way. So it is 31.61 inches. So those are the two numbers I got for steel and aluminum. If you look to, say, the delta steel over delta aluminum, which is the 10.90 over 31.61. So it is almost 1/3. So it is 10.90 divided by 31.61 divided about 1. Okay. Okay, or is equal about 0.3448, which is about 1/3. About 1/3. So which is 0.33. So this is the ratio. Okay, delta steel and delta aluminum. So the steel. So the modulus of elasticity that for concrete, the number that we said it is between 2 to 7 million psi. This is the number that it's a function of f sub c prime. And as I said, that the equation, that the empirical formula that ACI developed for us, that E sub c is equal 57,000 square root of f sub c prime. This is the empirical formula, and the Modulus of Elasticity will come in psi. So this, it must be in psi, by the way, psi. And don't tell me it's under the radical, so the units will not. This is an empirical formula, so units are not really important parameter or a parameter in the empirical formulas. Okay, so so this is something that when you receive it, if I remember correctly, there was a problem, and I believe some of you already sent it to me. I believe in one of the mini exams, maybe mini exam number 1 or 2 or 3, can remember. It's asking about the deflection, maybe 2 or 3, I believe. Maybe I don't have it with me here right now, but basically it was a beam, if I remember correctly, and for those of you who attend the first time, I can do it very quick or put it very quick. So delta. So if I have a beam, okay, a concrete beam, that it is part of a bridge design or part of, and let's assume that L here is equal 200 feet, and the cross section of the beam is 12 by 18 inches. Okay, ignore the reinforcement. This is concrete. Okay, this is a concrete beam. So this beam will deflect under its own weight as shown. And assuming that the F sub C prime is 4,500 psi. Okay, and so delta max under its own weight, under own dead load, is most nearly, and again I will ask you to give me 4 answers: A, B, C, D. Okay, and I need it to be in inches. Let me give you 3 minutes because this is a little bit longer than, or make it 4 minutes. Right now it is 10:46 California time, so 10:50 I will stop now. Okay, time is up. Okay, right now I gave you 4 minutes. So the first thing that we need to know, or we need to get first, or we should know, is the equation. And you'll find that the delta max, the maximum deflection, it will occur at the center of the beam at L/2. And the equation for the maximum deflection at the center is given by this 5WL to the fourth divided by 384 EI. If you look to the steel manual or any book, including mine, chapter 4, you will find there is one equation given like this. Okay, so since I got the proper equation and I know the maximum deflection is asking the maximum deflection under its own weight, so I need to get this. I need to get W, I need to get L, I need to get E, I need to get I. And L is easy, given 200 feet. I is easy because I have 12 inches by 18 inches. So it is BH cubed over 12. The famous formula for a rectangular section is BH cubed over 12. We should not forget that. Okay. E, I know F sub C prime. So I will use the empirical formula. I will say that the E sub C is equal 57,000 square root of F sub C prime. F sub C prime is given 4,500, 4,500, sorry. Okay, 4,500, yeah, 4,500. Okay, so it is 4,500, and I'll take the square root and multiply this by 57,000. So this is about 3.8 million psi. 3.82 times 10 to the 6 psi. So I got the E. I is very easy. I is equal BH cubed over 12. Here it is. I is equal B, which is 12 inches. 18 cubed divided by 12. So it is 18, enter, and the cube. Help me because I just, okay, and 12 will cancel out. Okay, so it is 5832. 32 inch to the fourth. Correct me if I'm wrong, okay? So I got I got E, L is known, which is 200 feet. We still have W. W is the unit weight per linear foot. So if I took 1 foot of this beam, I can calculate W, which is the unit weight per linear foot. I have 12 inches, so I say 12 inches divided by 12 inches per foot times. The depth is 18 inches. I will say 18 inches divided by 12 inches per foot. Okay, and I'll multiply this by 1 foot length. And I know concrete, I will assume this is 150 pound per cubic foot. So if you do this, so per 1 linear foot, I get W to be 18 divided by 12, and you multiply this by 150. So this is 225 BLF, pound per linear foot. So this is my W. So right now, before I proceed with the calculations, we got all the parameters, and I will write it down on the following page. I write down all these things, the computation, because units are very important in this case also. But I need to get some answers. If you already did some calculation or did some computations, so I would like to see your numbers to see who is the winner. And the winner will take him to lunch, but after this coronavirus is gone. Okay, so I need units, my friend. I need units. I need units. Okay, don't give me just numbers. One of you is giving me 1655. 1655 what? And I got another answer, 363 inches. This is an answer from one of you. Already I put inches here, so okay. Anybody support our friend, or anybody give another answer, please? Let me give you another minute. I gave you everything almost. So we need somebody to support this answer or give us another answer. We got completely different number, 21.8 inches. Okay. So 21.8. So we have another answer from another friend. Let's see who is going to be the winner. The winner will take him to lunch. Don't worry. I will take you to lunch. But after this bending is over, just let me know, and don't worry. I will take you to lunch. Or you will take me to lunch, whoever is available. Or okay. Here is another answer. That's good. I got 363 inches. Okay. And I got 2.52 inches. So 363, so 2.5. Okay, 2.52 and 21.8. 21.8 and 2.52 inches. And 363, there is another couple answers came to support this answer. Oh, 1.76. Oh, so we have another answer. So we have all answers. 1.76 inches. Okay. 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 The units, I told you the units are very, very important. So, especially with the distributed load. So again, I need you to know how to determine the distributed load per unit length. This is something that I need you to master that, because they can give it you in steel or concrete or wood or anything. So what I did, I said, okay, this beam is 12-inch wide and 18-inch depth. So what I said, that if I have 1 foot length of this, how much the W will be? Because the equation delta max or delta max is equal 5 WL to the 4th divided by 384 EI. Check this equation, please, to make sure that I didn't write it wrong. So the W in this case, W is, I said that I have the dimension, which is the cross-sectional area, is 12 inches per 12 divided by 12 inches per foot times 18 inches divided by 12 inches per foot times, I took 1 foot length. But I know this is concrete, so I said I took 150 pound per cubic foot. I don't know if all of you use 150 or not. Maybe some of you use 145. Between 145, gamma concrete, as all of you know, gamma concrete, normal weight concrete, is between 145 to 150 pound per cubic foot. It's acceptable to write it that way. Make sense? So this is the number that I got to be the 225. Let me do it one more time. This will cancel. So it is 12 enter, and it is 150 times. So it is 225. 225 PLF, pounds per linear foot. Every 1 linear foot of this beam weight, or this beam, is weighing 225 pounds. So if I plug it into the equation right now, and here we go. So it is 5, and this is 225, and I would say pound per foot. L, I gave it to you 200 feet. 200 feet. and this is to the fourth power. The equation is to the fourth power. If you go back to the differential equation and integrate twice and put the limits and all these things, you will find that the length is to the fourth power. Because if you remember, the cantilever beam was to the third power, BL cubed. So concentrated loads, we are dealing with L cubed. But distributed loads, do you remember L cubed? Because this is a concentrated load. Distributed loads to the fourth power. I need you to remember that. So this will be foot to the fourth power. But I have bound bilinear foot here. So foot will cancel with this. It will give you what is left here, foot cubed. This is why I multiply 1728 inches per cubic feet, which is 12 inches per foot. If you cube this, you will get 1728 inch cubed over cubic feet. So right now, this will give me foot to the fourth power. This will cancel with this, will give you foot to cubed, and this will cancel. So the numerator right now became inches. So remember 1728 here, this divided by 384 times. What is E? Do you remember E? 3.82 million PSI based on the empirical formula. So 3.82 times 10 to the 6. I is BH cubed over 12. Here it is. BH cubed over 12, which is 5832 inch to the fourth power. This, by the way, PSI. It's very important with the unit. And finally, the I is 5832 inch to the fourth. Let's look to the units right now. What we're supposed to get. So this is inch to cubed, inch cubed. Cubic feet is done. So, and I have a bound, and this is bound per square inch. And this is inch to the fourth. So, inch to the fourth, and this is bound. Bound will cancel with bound. And this is inch square. Inch square, and I have inch to the cubed here, it will give you inch to the fifth. Inch to the fifth, I have inch to the fourth, so will give me inch at the end. Units are very, very important, and nobody above mistakes as far as units. We do mistakes. So if you do this, let me do it, and after that you can tell me if I did a mistake or not. 5, enter. 225 times. And 200, enter, to the fourth power. And 1728 times. And the 384 divided. 3.82 divided. And 10 to the 6 divided. And 5832 divided. I got a number. Okay, anybody can help me with? Okay. May I answer this phone? I will come. Okay, sorry, I was answering a phone, that urgent phone. Okay, so anybody got an answer here? Let me see if somebody did the math. Alice, first of all, any problem with units, with the units or the numbers I put, number one. Okay, so about 363. Okay, so and this is what some of you got, which is good news. Okay, 363.58 point whatever is. So we need to pay attention to units. Units are very, very important, by the way. 363 point something, and this is what I got also, 0.58 or so we need to pay attention to that, because the 7 to 8. I'm doing it one more time. Yeah, okay, that's fine. Okay, so any question about that? So the deflection calculations and the modes of elasticity. Okay, thank you very much. Is this a reasonable amount? No, it's not a reasonable amount. Okay. Because unbelievable amount. Our friend said that because 363 inches, it is a huge amount of about 30 feet or so. So this is not reasonable, and that's why the cross section, first of all, I gave you a very, very small cross section for the span. Number one. Number two, this is a plain concrete. Normally we don't do that. Will be a lot of reinforcement and a lot of things, but for the sake of no, this is not reasonable at all. In fact, this amount of deflection normally about, okay, if it is a bridge, it is L over 800 to L over 1000. This is a maximum deflection permitted. So if the length is, if I take this is the standard, by the way, the AASHTO stand between L over 200 to L over 1000. So if L is 200 feet, so in this case, so it is 200 feet, sorry, 200 feet divided by 800 to 200 divided by 1000. So this is going to be a quarter, so a quarter foot, okay, which is how many inches is that? A quarter, so this 3 inches to 2/10, okay, which is the L over 1000. So it is 2/10, so it is 2.4 inches. So the acceptable deflection is between 3 inches and 2.4 inches, okay, based on the AASHTO, this AASHTO criteria, by the way, AASHTO criteria between L over 800, the maximum allowable deflection, okay, it is L over 800 to L over 1000, okay. So yeah, this number is a huge number, but okay, next time I will give you probably smaller span, and or I make the cross section much deeper. So in this case, this cross section should be okay, much deeper than that in order to achieve. But thank you very much for asking this question. This is a AASHTO standard. It is L over 800 to L over 1000. Where L is the span length, in this case the 200 feet, so it is between 3 inches or between 2.4 inches to 3 inches is the acceptable range for the deflection. And as all of you know, which I mentioned this before, that the deflection under its own weight, the beam under its own weight, normally we build the beam on the other direction, which was called, okay, camber. We need to, because we don't like the beam to deflect under its own weight, to be like this. Even 3 inches or the 2.4 inches, we don't allow that. We don't allow that to be as shown like this. We don't allow this to be happening like this, that the beam will come down under its own weight, no load on it. This is 3 inches, 3 to 2.4 inches, or 2.4. Let me start with the lower limit, 2.4 inches to 3 inches. Even we don't allow this to be like this, because there is a concern about the water, as I mentioned last time, the bonding, okay. The water may accumulate here, so it is and this will increase the deflection. even more, because if it's raining or we have some kind of accident or some kind of whatever situation, so we have some water here. So this water will increase the dead load on the beam, and the beam will deflect even more. So and again, psychologically, it's not really appealing to the eye of the driver. The beam is coming down 3 inches or 2.4 inches. So this is why they came up with the camber. Okay, the camber diagram. That the beam that we do it that way, and some of you already. So we build it that way. We build the beam to be concave up. Okay, to concave up like this. Okay, so concave up. Intentionally, we put the forms like this, and we have a camber diagram, and so the contractor has to form the camber beam and so on. And some of you already did that. Probably I did this a lot. So this beam, okay, we build it that way. So under its own load, I know it will come down the 2.4 or so. It still have, it will come down. Probably it will be like this. Will come down a little bit under its own weight. It does have a little bit of camber, okay? A little bit of camber, okay? So the water, if there is a water here, the water will drain into the proper direction, because we have a camber, and the water will run this way. And also, it is not going to scare the people. Mr. Mansour, who will see a beam like this coming down, is still safe. The 2.43 inches is still safe, by the way, but it's not really appealing to the eye when you see a bridge is sagging down and you say, oh, your wife is, wait a second, don't go over this bridge. This bridge will come. No, it will not come down. But the biggest issue is a water issue, and the hydroplanning and the additional load and all these things. This is why we provide some kind of camber diagram or a camber shape in order to accommodate or to be effective in draining the system quickly, to avoid any additional deflection and hydroplanning and all these things, safety issue. Okay, all these things are valuable discussion. I hope that you are agreeing with me. What else? The chapter that I scanned and sent it to you, I apologize that the quality of the scanning probably, I don't know, the copy machine probably, when I looked at the scan, when I open it, but just print it, and I will get the PDF during lunch, and I will send it again one more time after lunch when I go and pick up the PDF from the other place. The shear and read it very well, by the way, until when we meet next time. So after you receive it, if you print it already, that's good news. If you you'd like to wait until you receive the PDF printed, and it does have a lot of information and a lot of problems. Some of them we talked about it today, and some of them already we talked about it before, and some of them we did not touch it at all. But I will be glad to go over this next time when we meet again in July 4th. 4th of July, I know, is a holiday, but the fireworks will be in the afternoon, so you're still able to attend the class with me from 1 to 4, as I mentioned, on the 4th of July, which is going to be, I believe, Saturday. Yeah, Saturday, that's correct, Saturday. So Saturday between 1 to 4 California time, using the same ID. You don't have to enter another ID or let me throw something here very quick. I was discussing something with somebody, I can't remember who, and if you do have a frame like this, and a frame, basically it is structure consists of beams and columns. Here we have only one beam and one column. So I have a vertical member, which is a column, and the horizontal member is the beam. And I will call this is A, and this is B, and this is C. And let's assume that we do have the following load. Okay, I have only one load acting at the free end, and the load is a concentrated load P is equal 4 kips, and this is C here, and C. So, and this is 12 feet, and the height here is 20 feet, or make it 28 feet to make it to proportion. So the height of this column here is 28 feet, and this from here to here is 12 feet. Okay, so this is frame, and um, um, and many questions could be asked related to this. You can say that the M max, the maximum moment at B, and for answers, maximum bending moment at B. He can ask you what is the maximum moment, maximum moment, sorry, I should write the moment. Maximum moment at A is most nearly, and also for answers. And also, shear moment diagrams could be part of this question. He can give you a draw shear moment diagram, or in this case, in our case, I will ask you to draw it, but shear diagrams and moment diagrams. He will give you 4 diagrams: shear diagram and the moment diagram. Okay, shear diagram and moment diagram. So four problems, if you like to call the problem number 1, problem number 2, and problem number 3, and a problem number 4. So what is the maximum moment? Maximum moment at point B. B as in boy. Okay. Is it 4 kip feet or 24 kip feet or 48 kip feet or 72 kip feet? Okay, I gave you 4 answers, and the maximum moment at A, I will repeat the same values: 4 kip feet, and this is 24 kip feet, and 48 kip feet, or 72 kip feet. Okay. So what is the answer for question number 1? Either A or B or C or D, or if you believe none of the above, or there is no any answer to match this. Okay, let me see if, okay, great. Okay, we got a lot of, okay, so the answer is C. Okay, what about question number 2, the maximum moment at A? maximum moment at A. Okay. Okay. The fixed end here. Okay. So the maximum moment at A also I got some good answers or correct answer. It's still 48 cube feet. Now I need you to draw the shear diagram for this frame here, a frame that is fixed here and free at the other end, frame as shown. So I need you to draw the shear diagram and I need you to draw the moment diagram. So I will give you 2 minutes each, and since I don't, or I can give you 4 answers. Here we go. I draw the frames for you so you can sketch the shear diagram. Normally it is a V and the moment diagram is an M. So and this is A and this is B and this is C. This is C and this is B and this is A, C. And I can draw some diagrams for you, but let me give you a chance. I just made the problem right now because I had a discussion with somebody and told me that maybe he saw something, maybe he was dreaming about the exam and he saw a problem like this in his dream. So I told him, that's fine. I hope that your dream will come true. And let's wait and see until October 22nd or the 23rd and see if the dream will come true or not. As far as this is a moment, I draw just 4 moment diagrams. As far as the shear, um, and the shear is in kib, and the moment in kib feet. Okay. Okay, so I can make the frame a little bit darker. So when you receive it, it will be very obvious. Oops, sorry, it is my marker is. Oh, it seems that this marker is not making a good job, so I need to make it by hand without straight edge. Okay, sorry for this mess, but okay, so we do have 4 answers. Answer A or B or C or D for the shear, and this is also answer A or B or C or D. And this here, until I bring the problem, I told you that I promise you with the problem during the break. Let me get it very quick. Okay. So this is the original frame. So when you receive the problem, I will scan it before I go to lunch today. I will scan it and send it to you before I go to lunch and get the PDF. So Look at it and tell me what do you think, what is but let me draw the other problem very quick. At least you can start working on it. And so it is a beam that shown as it's fixed from one end, totally fixed, okay, and it is simply supported here, has a roller, but if we look to this beam, by the way, as is, right now, this is statically indeterminate to the first degree. So it does have a distributed load along one portion of it. It is a 5 kb per linear foot. Probably my scale is not a little bit. This is 4 feet. Okay. And at another 4 feet, I need to move the other end. Okay. This beam, by the way, as is right now, if this is A and this is B, it is aesthetically indeterminate to the first degree. Why? Because I have 3 unknowns here and 1 unknown here, so 4. So 4 unknowns, because I have 3 unknowns here. I have A sub y, and I have A sub x, and I have the moment at A. So if I keep the beam like this, so this is statically indeterminate to the first degree. Because 4 unknowns and the 3 available equations. So in this case, since already I wrote something here, let me make my dimensions a little bit smaller so it can fit. So this is 4 feet. The first 4 feet it does have. In order to make this beam statically determinate, we can introduce what is known as the internal hinge. Internal hinge. This is a hinge. Okay. At point C. And the hinge is also 4 feet away. And there is a concentrated load here, 20 kips, that it is only 2 feet away. And there is another moment here, a concentrated moment. It is 50 kip feet. And this moment, it is 2 feet away from either end. So this is what I needed to work on it if we didn't finish it. So it is 2 feet and 2 feet and 2 feet. And the beam is so I have a concentrated load of 20 kips. So this is A, B, C, and this is D, and this is E. So at D, there is a concentrated moment as shown, 50 kib foot in this direction, clockwise. So, and a distributed load, 5 kibs per linear foot. Okay, and tons of questions could be asked. For example, what is the maximum moment M A, or what is the moment at A? Okay, or what is the moment at D? What is the moment at E? You can ask all these questions. Okay. So I need you to do all this. Now, by giving this internal hinge, okay, this is an internal hinge. Let me just remove this arrow here. So this is an internal hinge. So right now I have 3 unknowns, still 3 unknowns here. I have 1 unknown here, by the way, which is B sub y. Why this is? Because this is a roller support, A roller has only one reaction perpendicular to the contact surface. So he might ask you what is the A sub y, the reaction or the vertical reaction at this, how much? He can ask you, obviously by inspection, A sub x is equal 0. A sub x is equal 0, so the component in the x direction here is equal 0. But he can ask you about the reaction here, B sub y, how much? So if we can get the moment at A, M sub A, and M sub D, it could be M sub E, many questions that could be asked. Reaction, and also what I needed from you to prepare is to draw shear moment diagram for this. Draw shear and moment diagrams, okay, which is a V and M for this beam. So if we can draw the here we go. Okay, so right now we need to draw the shear and moment diagrams for the given loading as indicated here. And there are tons of problems. Every single book available in the market or structural analysis books. Normally, I enjoyed my structural analysis books, the one I used it way back in Las Cruces, New Mexico, or here at CSU Fresno. And there are tons of problems. And so, but if you understand the concept, so this is V and this is M. V in this case, I will put it in kibs, and the moment is a kib feet. And remember the two equations that I wrote before, dm by dx equals V. The shear value is equal the slope of the bending moment, or the slope of the bending moment diagram is equal to shear. And that second equation, dV by dx, as normally I write this first, is equal negative W. If we are able to recognize these two equations and understand them, we will be able to. So please go ahead and do a lot of things. But by putting this hinge here, the internal hinge, so I have four unknowns. I have A sub x, A sub y, and M sub A, and B sub y. So I have four unknowns. And I have only three equations, which is sigma force x, sigma force y, and sigma moment. But I do have a conditional equation. This conditional equation is one hinge. What do I have at the hinge? I have the moment is equal 0. This is like the hinge in the door, in any door of your house. The hinge, I can open and close the door. Why? Why I'm able to open and close? Because the moment is equal 0, except the friction and the air. Forget the friction resistance, okay, of the hinge itself, especially if it's rusty, or if it is this door, it is a bathroom, and there is a lot of, or shower, and there is a lot of rust on the, so probably okay, very difficult. But theoretically speaking, ignoring the friction and the air resistance, the moment has a value of 0 at the hinge, internal hinge. So this is a hinge. So I know the moment. So this is called conditional equation. So I have a conditional equation here that the moment here is equal 0. So by doing that, so four unknowns and three available equations, which is sigma force x, sigma force y, and sigma moment, and plus the one conditional equation, which is a hinge. In this case, we are 4 equals 4. So this is a statically determinate. So statically determinate beam. So you should be able to solve it, because all the problem that you will see in the AM is going to be statically determinate. Statically determinate. So in this case, you should be able to solve it. Okay, going back, so we can wrap up this, so we can go and scan the stuff and send it to you, so you can start working, because you promised me you are not going to stop working from now until October 22nd or October 23rd. It depends on your exam, because as you know, and I don't know how many of you already enrolled already on the so the exam, as you know, they open it according to their website. I don't know, normally I check it from time to time. I check the NCEES website, please. Okay, so June 1st, as far as I know, they opened the enrollment, unless they changed their mind and they did something different. This is the latest information I have, or the latest information that my webmaster put it on the web. So, and if you go to our website and they click here at the bottom, by the way, the NCEES, it should take you the NCEES. So please check this website from time to time. Here it is. October registration for October 20B exam is currently open, and it will be closed 3 p.m. of August 20. Please note. So, and here it is. They give you a lot of information. Please read it carefully and you accept that. And as you know, the exam will be given on the 22nd and the 23rd. So there are some exams on the 22nd, some exams on the 23rd. I try to read all the information and the notes, or sorry, news, and any news or any thing. Okay, so. Okay, so CBT, they moved it to October. Some of them CBT already started, as you know. So please do your best. Do your best, okay? So going back to the problem here. So this one here. This conclude our discussion here. So the shear diagram. The shear diagram is a shear diagram A or B or C or D. Which one is the best? Which one is the correct one? And I try to put signs, positive, positive, negative, negative, positive. I try to do my best here. So I'm looking for problem number 3 for this given frame here. Which one is the correct shear diagram? V in Gibbs. Okay, based on your selection. Let me go to the questions. Okay, I got only one answer so far. I got, okay, another answer. Okay, okay. Any suggestions? Any other suggestions? Okay. Okay. A lot of answers, but if you look here, you'll find that the reaction at A sub y is equal 4 Gibbs, and A sub x is equal 0, and the moment at A, M at A is equal to the 48 Kb feet, the one we agreed upon. So for the shear, this vertical column AB, it does have axial load only, which is compression. So it doesn't have any shear. It does have shear only if A sub x exists, but we don't have any components. So there is no shear here, and I will come here. I will go up 4 Kibs, which is this one here coming from here, 4 Kibs, and go straight until I hit Kib, 4 Kibs coming down. So the answer is D. Okay, so the shear diagram is D as in Dr. or David. And when you receive it, look at it again and let me know if you disagree with me. Don't take me to court. Okay, we agreed last time, I believe, or the time before, no court this time. So we're going to resolve our differences here without going to the court. And if I'm wrong, I'll say, oh, I was wrong. Okay. If you are wrong, you say, yeah, I was wrong. And this is our objective here, is to do our best to, okay, and nothing wrong if we did a mistake here. Okay. What about the bending moment diagram? So we can conclude. So I can go and scan it right now. Okay. Bending moment diagram. Okay. Either A or B or C or D. By the process of elimination, I don't know if you noticed this is a curve. I drew it like this, second degree, a curve. Obviously, I have a load, a concentrated load. So the shear is 1 degree higher. So this is straight line here, has zero slope. And as you can see here, by the way, dV by dx is equal negative W, this equation. The slope, what is the slope of this? Is 0, because there is no load from here to here between B and C. Okay? So this is a concentrated load. So the degree, the shear is 1 degree higher, or the degree of the shear is 1 higher, and the degree of the moment will be 1 higher. This is horizontal, so it cannot, so this is out. Parabolic only if the load is a distributed load, like this portion of this bending moment diagram that you are going to draw. This is a distributed load. You will find that the shear is linear and the moment is a second degree. You will find that after you draw it, okay? So the process of elimination is also a powerful tool. I need you to be aware of that. So this answer is out because of this shape here. I gave you these two questions first so you can figure this out, by the way. The moment at B as in boy is equal force times distance. It is 4 times 12 is 48. So the moment here is still the same. The moment here is still the same. The moment here is still the same. Until the moment here is still the same. Okay? So I still have 3 answers. Either A or B or C. I get rid of the... By the process of elimination also, the answer B is out. Why? Because he's showing no moment here along this portion of the frame here, which is portion of this. No, the moment at C exactly is 0, yes. But the moment here is 1 foot away from C is 4 times 1 is 4. 2 feet, 4 times 2 is 8, until the maximum here is 4 times 12 is 48. So the answer B is out. I need you to remember this process of elimination. And you will learn this, okay? So I still have 2 answers, 50-50. And as I always say that, just if you are able to use a process of elimination and get rid of 1 answer, at least 75%, 3 answers. If I get rid of 2, I have 50-50. And that's much better, okay? So I will pick one and pray to God, and may God accept my prayer. But if I practice enough, I will still pray to God, but I need between A and C. Here he showed only the moment along the beam portion, the overhang, if you like to call it, the beam portion. But this vertical column also has a moment. It does have a moment. In fact, the deflected shape of this, by the way, is like this. I'm just exaggerating the deflection. If you push this down, I'm just very, very exaggerating, very, okay. So this is compression, and this is tension. And this is tension, and this is compression. What kind of bending moment is that? Do you remember? The positive bending moment is the heavy phase, compression, tension. The other one, it is tension, compression. So this is a positive bending moment, and this is a negative bending moment. Negative M, sorry. Let me put I thought, okay. So So the bending moment here is, this is going to come down where tension compression, like a cantilever beam, okay? So, and the moment along this is constant, by the moment along this here is constant. In fact, if you like to look at differently, you can say that this is equivalent to what? To a vertical column. I can get this load, put 4 kips here and subtract 4 kips. I can say this is as an axial load and bending moment. This is equivalent to this. So the bending moment here is constant. This bending moment here is constant. This is why the answer A is the correct answer. This is 48, the maximum here, and 48. So the bending moment at this corner is the same, okay, along the cantilever and along the vertical column. So the answer A is the correct answer, okay? If you disagree with this, please let me know, and I will go and scan this right now. And thank you very much for coming today, and I hope that everybody is, as I said, that's studying very hard and be ready for the exam. The exam is coming. If you think that they are going to postpone it again because of this corona stuff, no, I don't like you to assume that. I need you to assume that the exam will be held on time, and you will go to the exam and ace it one time and one shot. And I hope this is going to be the last exam as far as a national exam, to take it and forget it and move on. So I will scan this. I believe I ended with 8 sheets. I will scan it and send it to you. And thank you very much again. If you need anything or any clarification, please email me, and I will do my best to come back to you as soon as I can. And I hope all these things, if you disagree with me about any of these items I discussed today, or if you found a typo or mistake or an error, let me know. At least I can correct it next time. And I don't mind to correct myself. If I did a mistake, I will admit it and keep going at least. And the same story with you. If you did a mistake, admit it and keep going. Okay. Thank you very much again, and stay safe as you can, and stay healthy, and stay preparing for the exam. Thank you very much. Bye-bye. I have a class this afternoon, a surveying class. This for the California Special Surveying Exam. The ID is different, by the way. The ID is different. It's not the same ID. So if you'd like to join me at 1 o'clock, let me see if I have the ID handy here. I believe, yeah, surveying is ID. This is the last session today. Surveying ID. It is 958-885-587. Today is the 20th. Yes, from 1 to 4. Yeah, from 1 to 4. From 1 to 4 p.m. Pacific Standard Time. So I will, say again, www.joinwebinar.com. Joinwebinar.com. And enter the ID 958-885-587. That's correct. This is an Egyptian 5. Let me make the 5 is a little bit better. Okay. So, and if you do have any problem, call me and I will, but let me leave this for 1 minute here. So you can copy it, and after that you can, this is only will be limited to surveying for the Special California Surveying Exam. If you are interested, you are very welcome. If it will not help you or it doesn't have any impact on you, so focus on the studying of the other stuff that will benefit you the most. Okay, so I will end the session right now, and I will go and scan these things and send it to you. Thank you very much. Bye-bye.